Alright, so we're going to look at factoring quartic polynomials. One technique, which is rarely useful, but it's possibly useful, is to change x squared into a y. Because if you look at this, this looks like a regular trinomial, except that these two exponents are twice what they normally are. So by doing this, this becomes y squared minus 7y plus 10, which we can factor very easily by looking for the factors of 10 that add up to be negative 7, which is negative 2 and negative 5. They add up to negative 7, 2 and 5 don't, 1 and 10 don't, negative 1 and negative 10 don't. You don't have to go through listing all of them, unless you wanted to prove this was unfactorable, but it is. So this is y minus 2 and y minus 5. But this would not be our final answer, because our answer should be in terms of x squared. So we can now substitute back in x squared, and we'll get x squared minus 2 and y squared minus 5. Now, neither of these are difference of squares, so they can't be factored any further. There's also no GCFs. Let's take a look at a different way to do this, which is always useful, which is great when these things are factorable. So we have x to the fourth minus 7x squared plus 10. This can be factored by grouping. So let's look at AC. AC is the product of the first term and the last term, which in this case is 10. 1 times 10 is 10. We're going to look for two numbers that multiply to be 10 but add up to be negative 7. We already found them over here. So it's negative 2 and negative 5. They do. So we can break up the middle term, or B term. Came out kind of looking gross, so let's fix that. That's x, still not looking good here. Let's try that again. X squared minus 2x, x to the fourth minus 2x squared minus 5x squared plus 10. And I put the 5 on this side because it has a common factor with 10, but I think the 2 also does, so it should work either way. So grouping these two terms together and these two terms together, this has a GCF of x squared, so let's factor that. And this has a GCF of 5x, just 5. So after factoring that, we get this, and they have a common GCF factor of x squared minus 2, which should look familiar, and a remaining, I left that out, and an x squared minus 5, which is our remaining pieces here. So that gives us x squared minus 2, and x squared minus 5. And the question becomes, should we use substitution, or should we use grouping? And I would say grouping is probably the better choice, because it'll work more often. Let's look at a couple more examples that are a little bit more interesting, both of which substitution would not really be useful for. So in this case, we have to, this is not a quartic polynomial, but it does have a GCF, and its GCF is x squared, which leaves over 2x to the fourth plus 13x squared plus 6, which is a quartic polynomial, which has no other GCF, so this can't be factored like a regular trinomial anyway. It has to be factored using grouping, and if it has to be factored using grouping, there's no point in substituting. So let's take a look. AC in this case is equal to 12. We need two terms that multiply to be 12 but add up to be 13, which should stand out as 1 and 12, not negative 1 and negative 12, not 2 and 4, 2 and 3, not 2, 2 and 6, not negative 2 and negative 6, not 3 and 4, not negative 3 and negative 4. I think I covered them all. So this is the only one that adds up to be 13. So we will have to separate our terms a little. So that's x squared, 2x to the fourth, the 6 is still here, and now we have to separate this. I think the 12 should go with the 6, and the x, or the 1x, should go over here. Does it really make a difference? Sometimes. But if you can find the common factor, you should split them up that way. So grouping these two terms, we're going to take our GCF. Alright, so the GCF of the first term here is just x squared, which leaves over a 2x squared and a 1, whereas the other one's GCF is 6, positive 6, which will leave over a 2x squared and a positive 1. So looking at this, we have a common factor here, which can be factored out. So that'll leave us with x squared times 2x squared plus 1. And this remaining part here, that is x squared plus 6. So that appears to be fully factored, as this does not have a GCF. It's also not the difference of squares, and neither is this. One last example. We have a quartic polynomial, has no GCF, so it looks like grouping is the way to go. We can, again, substitute, but I don't think it will do anything. Matter of fact, let's do that. We'll call this y squared, and we'll call this y. I don't believe it's going to help us in this case. So in this case, x squared is equal to y. So we need to use grouping anyway. So AC is equal to negative 315. Oh no. Yeah, negative 315. So we got to look for the factors of... Oh wait, I made a mistake in this problem. This was supposed to be a 58. Excuse me. Fix that now. Alrighty. Now everything should be okay. So the factors of 315 that were 5 and what was the other one? 63, I think? 63, in which case we want a bigger negative number. So these are the ones that add up to be negative 58. So let's continue. So that's 7y to the fourth, squared, excuse me. We substituted specifically to get rid of that fourth power. Squared minus 63 and 7 have a common factor, so let's put the 63 over here. Put the positive 5, whoops, y, with the 45. The GCF here is 7y, leaving over a y minus 9 and a whoops, the GCF here is a 5, so that's 5, leaving over a y minus 9. That's our common polynomial factor, so we have 7y plus 5, and that's the remaining piece, and y minus 9. Now we would substitute back in here, and that would give us 7x squared plus 5 and x squared minus 9. Now in this case, the substitution actually was not as helpful. It didn't do much at all. Matter of fact, it made this piece possibly unfactorable because people might not notice that this is a difference of squares. So this should actually finally factor to be x squared plus 5 times x minus 3 and x plus 3. So that's this one finished. So yeah, I would recommend not using substitution. It could be helpful, but sometimes it's just not useful. Grouping is always useful. Alright, have a nice day.